a predetermined set of categories of outputs which you know beforehand. Whereas in some cases where we have to work with continuous variables, which is basically looking at output which is a continuous value, there you will go with something like a linear regression. Or in fact, for numerical data, as we saw, a neural net is also a very good approach to looking at continuous data. So while we are on this topic, let us segue into a different topic which is of a lot of interest to several people now in what is known as deep learning. So what we do mean by deep learning, we will just go through briefly in terms of the theory so that you get an idea. Then we have shown how this kind of works for specific data set in this case. So what is neural net all about? Neural net is basically in a rough word, it is a mathematical formulation to simulate human brain. So human brain is basically made up of a set of what we call as neurons. And in neurons, typically what you have is something known as a signal receiver and a signal transmitter. And then there is a network of such nodes which are all connected to each other. So let's take a biological neuron. Biological neuron is basically a node which is like a nerve node. Then they carry signal away and to that node, and there are several neurons which are connected with each other. That is what is typically the structure of our internal nervous system. In the similar spirit, neural networks is based on the idea that you have several layers of each of these nodes connected to each other, and they communicate with each other via edges which are going between each of these nodes. And the simplest structure which works in neural nets is we have one input layer of nodes, one output layer of nodes, and then all the other nodes are in multiple layers between the input and the output layer. These are known as hidden layers. So in the hidden layers, when you talk about getting a idea of how many hidden layers are typically required, it is depends on your complexity of your algorithm or complexity of your data prediction, how many different what you call features you work with or independent variables you work with, and that dictate how many in hidden layers you have to work. So this is a rough comparison of how brain processes. It's a very powerful tool that the key scale comes from it being parallel and distributed. And each step here usually consists of simultaneous work across thousands of nodes where each of them is changing weights locally, and then that overall describes a change in the global behavior. If I were to understand a specific global equation which governs how it works, it doesn't exist. It is just that this input layer, output layer, multiple hidden layers, doing this iterative steps on looking at the different input samples and trying to come up with different weights for each nodes, they do multiple steps after steps till they stabilize and there is no more change. And then they say that, okay, this is your collection of weights, this is the neural net, which is your prediction model. That is what you're going to use for any future value. So in case of that, what is it? It's basically a way by which you are computing the different weights of the edges which feed into the function at each node. The functions can be of multiple types depending upon what you choose in terms of how you say a particular node is going to get activated and how is going to trigger change of weight in the next layer. Then in terms of the different kinds of problems it can handle if you have linear problems, it can handle, it can have, even the beauty of neural nets is we don't necessarily depend upon, like we saw in our surprise finding, right? That was definitely not a very linear model because we saw that error was up to 40% or something for linear regression. So it was definitely quite non-linear. So for such kind of complex topologies, neural nets offers a very good approach. So a typical neural net, as I said, is basically having one input and one output layer and the several hidden layers. So the individual computation function at each node, how it is computed as a function of several of the input weights that are coming to it. So here I want to mention one thing is there are multiple formats of neural nets. Let's not get carried away by saying that there is only this model, which is what we're talking about, is this multiple layers of uh, nodes, each of them connected to the previous node by weights and then weights readjusting based on the activation function. That is a very simplistic notion of a neural net. The earliest model of neural net was what is known as perceptron, which was what I was talking about. But several variants of neural nets have come up today, which are something like feed-forward networks, which are basically take weights only in one direction. Recurrent networks, self-organizing maps, Boltzmann machines, all kinds of variants of neural nets have come up. All of these are giving rise to this whole notion of what is called as deep learning. So as I said, if you were to get me an equation to describe how the function of the neural net is going to be represented, you don't have it. It's just that the collection of weights in each of them at a specific point of time is your model. So with each input data, it recalibrates. In the sense, the weights at each edges get recalibrated by passing on from one layer to another. And that is how you generate the target stabilized neural net, which is going to help you predict for a future. But beauty of neural nets is it is very good at dealing with uh, non-linear problems like which are not clearly separable by linear equations or linear hyperplanes. It's also good for dealing with a lot of continuous variables where we have continuous inputs like in control systems or in systems which are engineering driven. So in engineering schools is very useful. So in Veka also we have an implementation of the, as we saw, we have to look at when we take a data, you have to choose functions, multi-layer perceptron. So wherever there is discrete variable or even continuous variables, it works pretty okay. But if you were to look at what that model looks like, it is difficult to pinpoint a specific equation among the variables or the weights which is going to describe. So just to get an idea of I'm just trying to see if we can visualize the. I'm just trying to see if I can visualize the neural net. I was trying to see if I can visualize the neural net which is created. Uh, Somehow not. Okay, let's say go equal to true. In the option you can go and say go equal to true. So it's still processing. See, neural net, because there are many networks and many nodes where each node has to perform computation, it takes a long time to do that. So in this case, we're talking about a single hidden layer uh, net. Maybe we'll stop here. We'll do a percentage split instead of cross validation. Yeah. So you see the neural net that is generated here. This is the node values at each intermediate node. These are the output variables. You see the error here. This is pretty bad in terms of what it's been able to do. Yes, so I think this here now we got a good sample here. In this case, we're able to get a decent, we only have one misclassified instance for the test sample. So if you see here, what we've done is we have tried to experiment with different combinations of the inputs, either with split or with class validation. And we have found that in several cases, the multilayer perceptron is doing much better than what you did with, say, linear regression. So with that, we stop here. It was basically giving you arms to extend your potential for different categories of supervised learning. We started with Bayesian, when we went on with linear regression, then we went on to uh, logistic regression for discrete variable, then we went on to neural networks for all kinds of supervised learning techniques. So it is very important for you to understand that, as we discovered, in some cases the other model is better than the other. So you have to do that experimentation. That's why it's a toolkit. The idea for you is to get equipped with underlying logic. While in neural net there is absolutely no notion of equation, but the idea is collection of weights at each node together represents your model. Any questions at this time? We will go through some more tomorrow, which is on decision trees and random forests. Any questions? I think you may be now very much useful. You may want to check out an experiment yourself. That's what I would suggest, rather than this, because now you're equipped with a lot more algorithms. Clear? Okay, we'll stop here.